right, good morning, everyone. Thank you for attending this technical session. If you could please all mute yourselves so we can listen to the video and then the discussion later, that would be greatly appreciated. So today we will be discussing concepts of programming HPC for GPU accelerated infrastructure. This collection of talks presents the main concepts of HPC programming by outlining how GPU acceleration is exposed in general purpose programming languages. The NVIDIA platform acts as a bridge between the applications and the device-specific implementation on GPU hardware. The talk focuses on the most recent programming practices for today's accelerated applications, whether on-prem or in the cloud. NVIDIA Modulus is a neural network framework that blends the power of physics and partial differential equations with AI to build more robust models for better analysis. Whether you're looking to get started with AI-driven physics problems or designing digital twin models for a complex, nonlinear, multi-physics system, the talk on NVIDIA Modulus and Reservoir Simulation pins provides insight to leverage accelerated PDEs in applications. Additionally, you will learn how to leverage RDMA-based technologies like GPU Direct P2P, GPU Direct Storage to accomplish low latency communication and reduce CPU overhead. Specialized network adapter cards like Socket Direct and Multi-Host further complement these goals by enhancing data throughout to GPU by optimizing PCIe communication, minimizing QPI traffic, reducing CPU utilization, and lowering latency. As you move from scale up to scale out implementations for your science and algorithms, you will find these talks beneficial to optimize compute, data movement, and computer science. So we have 4 talks for you today. The first is Programming the NVIDIA Platform, presented by Jeff Larkin. This is a 15-minute presentation, followed by Modulus, presented by Sanjay Choudhry, which is a 20-minute presentation. After that, we have the Reservoir Simulation with Pins, presented by Clement Etienam, which is a 47-minute presentation. And we will wrap things up with Optimizing Data and Storage Movement for GPUs, presented by Kashif Chauhan, which is a 36-minute presentation. Our first speaker is Jeff Larkin. He is the Senior Solution Architect focusing on programming the NVIDIA platform. Will you please remember to put your questions in the chat box so that we can address them during the presentation? After the talk, Jeff can also answer questions directly, but please feel free to put questions in the chat box addressed to everybody so that we can all see them and we can all discuss them. With that, let's kick it off.
Hi, my name's Jeff Larkin. I'm a principal architect in NVIDIA's HPC software team, and I'm going to talk to you today about programming for the NVIDIA platform and also about NVIDIA's Hbc Sdk. Here's the topics I plan to cover. First, talking about how you can program for the NVIDIA platform using standard programming languages. Next, I'll talk a bit about what we're doing to bring GPU supercomputing to the greater Python ecosystem. I'll highlight a bit of what we're working on in math, core, and communication libraries, and by showing you our developer tools. So to begin, let's talk about programming to the NVIDIA platform. So I want to start by emphasizing the word platform. We're often thought of as the GPU company, but in addition to our GPUs, NVIDIA has a portfolio of networking equipment, and we've also announced the Grace CPU as a data center CPU based on ARM that's coming in the future. And because we provide a full hardware platform, we need to provide a full software and programming platform that is coherent across all of this. The foundation of this strategy is our accelerated libraries, and we provide core libraries for data structures and high-level algorithms, math libraries for common mathematical operations, communication libraries for scaling out to the full system and even full data center, and also abstractions for data analytics, AI, and quantum. On top of these libraries, we've built 3 approaches that you can use to program to the platform. And I'll stress that each of these can be mixed with every other one on this slide. So it's not a matter of choosing a path and staying in that path, but in fact, all of these can be mixed together. As a starting point, we encourage developers to write their code using the tools that are available in their preferred programming language. And so Iso C++ and Iso Fortran both provide tools and capabilities for parallel programming directly in the language. Here on the top, we can see how a C++ standard transform can be used to write a Saxby operation and have it execute in parallel. In Fortran, you can see the do concurrent loop here. Do concurrent enables us to parallelize this code. And on the bottom, even in Python, using QNumeric as a drop-in replacement for NumPy, you can accomplish a lot of the same things. By focusing on the ISO standard languages, you develop a code that is parallel first. And so it's not a matter of porting to GPUs or porting to multi-core CPUs or whatever platform is coming down the line. If your code is already parallel, then it will run on any platform that supports ISO C++, ISO Fortran, or Python. Now, this is a strong starting point, and it's able to develop code that can run anywhere. If you want to optimize your code, or we might say specialize the code, you can do a little bit by using compiler directives like OpenACC and OpenMP. This is common for small optimizations like data movement, as I've shown here. Or if you've written your entire code to be parallel and there's certain regions that you want to get the absolute best possible performance, you can rewrite those specific functions using CUDA C++ or CUDA Fortran. And in doing so, you're able to take advantage of everything we have to offer, both in the hardware and the software. So we can expose new hardware features into CUDA C++ that may not make the other languages right away. And so you can really optimize your code. But all of these can be mixed together, so you can balance a high degree of productivity and portability on the far left with the best possible performance on the right, and choose where along that spectrum you want your application to reside. To support this, we provide our Hpc compilers. Here being NVC, our C compiler, NVC++, our C++ compiler, and NVFortran, our Fortran compiler. These compilers support our latest and greatest GPUs, and even include being able to automatically accelerate portions of your code for you to these GPUs. It supports all of the programming paradigms I've discussed, so Fortran, C++, C, OpenACC, OpenMP, even CUDA, C++, and Fortran. All of these are available in these compilers. Not only are they great GPU compilers, they're great CPU compilers too. They support compiler directives, automatic vectorization, multi-threading, and they're really comparable to other compilers on the market in terms of both capabilities and performance. And they're available on all of the major CPU ISAs, x86, ARM, and OpenPower. And the Hbc compilers are just a small part of our larger product called the Hbc Sdk. The Hbc Sdk is designed to provide Hbc developers all of the tools they need in order to be successful. It supports all of the programming models I've discussed, the standard languages, compiler directives, and CUDA C++ and CUDA Fortran. Provides our Hbc compilers, plus it adds the NVCC compiler from the CUDA toolkit. And the Hbc Sdk actually ships with a complete CUDA toolkit. We provide some core libraries for high-level data structures and algorithms that you will need to build your applications. The complete set of NVIDIA's math libraries to ensure that you have the best possible performance on common math operations like linear algebra, FFTs, and random numbers. Also communication libraries, and here we ship with a pre-built version of OpenMPI plus NVSHMEM and Nickel. And then, because you're only really as successful as the tools that you have, we do also provide profilers, the Nsight Systems Nsight Compute profilers, and also the CUDA GDB debugger. And all of this is one package you can download. It is 100% free, and it's downloadable from our website, or it's available in a container from NVIDIA's NGC registry. It can be installed via SPAC and is available on all of the major cloud providers. Hbc Sdk ships about 7 or 8 times per year, and as I said, it's completely free to download and to use. So I've said that NVIDIA encourages developers to use standard parallelism from their programming language in order to write their code. And this enables you to write code that is parallel by default, which means that rather than driving along in this lane where you're not able to run on platforms such as NVIDIA's, you're already from the beginning running in this kind of light green lane here, where you're able to run on our platform out of the box. Once you're on our platform, you can then decide how much you want to commit to specializing to get better performance on the platform. Maybe using OpenACC directives to get small optimizations to get slightly faster, or maybe even using CUDA C++ or CUDA Fortran to get even faster and closer to the speed of light lane. The point here, though, is that by writing standard parallelism, you're already on the highway, and then you can decide how far you want to commit yourself to getting into the progressively faster lanes. Using standard languages for parallelism isn't a new idea that we just came up with overnight either. This is something that we have dedicated more than a decade to developing. We have lots of people within the company from all parts of the company that attend ISO committee meetings and contribute to developing these languages. It's our belief that we can focus on innovating in the language to better support concurrency and parallelism, and in doing so, this is a rising tide that raises all boats and makes parallelism concurrency available to all developers. And this is all in open collaboration with partners or even competitors throughout the industry. It's really our past investments that have driven us to this point, and so although the features that I'm showing you have only been available in our compilers for about a year and a half, that fruit came from more than a decade of developing in these languages and working in our software stack and hardware to better support these languages. We've worked on a variety of major features that I have listed on the side here, and some of these are already in the language, and some of them are things that we're continuing to work on to bring into the language into the future. So let's start by talking about specifically about parallel programming in ISO C++. C++ 17 added support for the parallel algorithms library, which enables you to write code in a way that's portable and expresses the parallelism that's in your code. This supports both vector and parallel threaded concurrency, and this is something that we can leverage today using our compiler and our hardware to offload to GPU or to run across CPU threads automatically. C++ 17 also added forward progress guarantees and clarifications to the memory model that made parallel programming possible within that language. And at the same time, we began to make changes to our hardware to better align with what C++ was doing. So C++ 17 and 20 are things that we can support directly in our hardware and through our software stack. C++ 20 also added support for ranges, which simplifies iterating over a range of values and makes C++, I would argue, a little bit more familiar and a little easier to use in an HPC context. It also added the scalable synchronization library, which is something that you need in order to be able to synchronize across the thousands and thousands of threads on the GPU or even between the CPU and the GPU. And so we have support for those primitives in the libq++ library. Now, C++ 20 is the most recent specification, but C++ 23 is in active development, and we already have a pretty good idea of what will be in C++ 23. And for HPC programmers, I would say that MD-span is one of the most exciting features. It's a way to represent multi-dimensional arrays natively in the language. So gone are the days of manually calculating your offsets into a flat array. All of this can be handled nicely for you using MD-span. It also provides range-based parallel algorithms, which is a more convenient way to iterate over the parallel algorithms, and also extended floating point types. So specifically here, I'm calling out 16-bit floating as a format. And C++ 23 is not the end of the road either. We're actively working in the committee for the next version, which will be C++ 26. And there's some exciting features coming, including ways to express concurrency and asynchronous execution using senders and receivers, and even abstractions for linear algebra that are baked into the language. So we're definitely working to continue to provide features that are important to HPC programmers in the language. So that's the current and future state of C++. Now let's talk about what's possible today. So first I want to show you an application called Lulesh. Lulesh is a hydrodynamics mini application that came from Lawrence Livermore National Lab. It's about 9,000 lines of C++. And we worked with them to take their baseline OpenMP code and rewrite it using ISO C++. And here's the sort of representative code transformation that we saw. This is just one function here on the left out of those 9,000 lines of code. And you can see that it is using OpenMP in a very typical way. We have a parallel directive here to spawn threads. We've got a for directive here to say this is the loop to run across those threads. And there's even an ifdef here because we need to ensure that this single source code can run well, whether it's threaded or single threaded. This is fairly representative of OpenMP codes, and I will point out that if I wanted to use OpenMP to run this on a GPU, I could replace these OpenMP directives with the target offloading directives, but then you would need to maintain both sets of directives in your code for the CPU and the GPU. We rewrote this code with them to use standard C++, and that's the code on the right. As you can see, it's much more compact. It's easier to read and maintain. If you're not familiar with the modern C++ syntax, let me walk through it here. So the algorithm we're using is standard transform. So transform applies this lambda down here to every element in the data, and the reduction is saying here to apply this reduction algorithm, which corresponds to this loop down here. This code is fully ISO C++ compliant. It's much shorter, so it should be easier to maintain. And since it is ISO C++, it can be built by any ISO C++ compiler. In addition to all of those advantages, it turns out to be faster too. On this graph, the blue bars represent the GNU compiler, G++, and the green bars represent NVIDIA's NVC++ compiler. The first two bars are running on a modern 64-core AMD EPYC CPU, and you can see that the OpenMP version performs roughly comparably regardless of which of these two compilers you use. Looking instead at the ISO C++ version, you can see these three bars. The first two are running on the exact same CPU using the exact same version of the compiler, but using the ISO C++ version. So using G++, you can see we got about a 50% performance improvement, and using NVC++, about a 2x performance improvement. And this comes from a variety of factors, including eliminating various overheads from that the OpenMP runtime introduced, or improving optimization by the fact that we're in a single API rather than moving between C++ and OpenMP. What's really great about this version, though, is that I can take it, I change one compiler option and say, don't build for my multi-core CPU, but build for my GPU. And you can see we get a huge performance benefit here. So all of this with standard ISO C++ code, we see portability across different compilers and across different architectures. That's a mini app. This one I'm going to show you is a full application. That's Maya. Maya is a multi-physics application. It's developed by RWTH Aachen University. And it uses a variety of fairly complex methods, hierarchical grids, adaptive meshing, load balancing. It has a variety of numerical methods. Now, not all of these have been ported or rewritten using ISO C++ yet. I know the Lattice Boltzmann has, and one of these others, and I don't recall which. So the programming model is MPI. MPI is used not just to scale between nodes, but to support multiple GPUs, and then ISO C++ to expose the data parallelism. You can see that the ISO C++ code on the CPU, it runs roughly comparably to the OpenMP, but has the advantage that we can then take that source code, rebuild it, and you can see run on the GPUs that are available as well. And they even get reasonably good scalability up to 128 GPUs here. So this application runs quite well using solely ISO C++. And to give you an idea of the sort of refactoring they did, it looks very much like the Lulesh example. You can see our OpenMP pragmas here, and this is rewritten, and this time it's using the for each n operation as the algorithm. And that does kind of what it sounds like. It over the number of cells here, it applies this lambda function to each of those cells. Another code that I want to highlight is STLBM. This is a lattice-Boltzmann solver from the University of Geneva. The reason I'd like to highlight this one is this was done, completely without our help. They really wanted to be able to write their code to support a variety of architectures and not rely on any external libraries, non-portable extensions, or vendor-specific code. And so they chose Iso C++, and they have reported at two of our GTC meetings, the GTC Spring in 2021 and GTC Fall of 2021. I encourage you to go watch these talks because they go into a lot of detail about the sorts of transformations in their code that were necessary and performance, far more performance results than I show here. What you do see here is that they could take their single code, they can run it across all cores of their 2-socket Xeon, or they can run it on the GPU they have available. And so the author of this code and the person who spoke at these talks is Professor Jonas Lott. He categorized this as a paradigm shift in cross-platform CPU and GPU programming. So this is what's possible today using solely Iso C++. But standard parallelism is available in Fortran as well. It's not limited to C++. And we support it in our NV Fortran compiler. NV Fortran 20.5, which was from the May release in 2020, added support for automatically offloading certain array syntax operations and math intrinsics, such as matmul and reshape. 6 months later, in the 20.11 release, we added support for Fortran's do concurrent loop. And I'll show you an example of do concurrent here in just a moment. Do concurrent does enable us to build this code to run it on multi-core in threads or automatically offload to GPUs. And so you can write one source code that supports both of those architectures. We don't currently support Fortran's co-arrays, but this is something that we are looking at and plan to support in the future. And just like with C++, Fortran is not done its development yet either, and so there's support coming in Fortran, the next version of Fortran, currently called 202X, for reductions on do concurrent loops. This is something that was not supported previously in do concurrent. Previously, you would do a do concurrent followed by an intrinsic to do a reduction. But this next version supports this, and we have already added support for this subclause. Even though 202X is not fully ratified yet, we've already added support because it's such a critical feature, and we've already seen production codes using it to great success. So in terms of programming in Iso Fortran, here's an example of a fairly simple stencil operation that's written using do concurrent. If you've not seen this syntax before, traditionally with do loops, we would have an I loop and a j loop nested together. With do concurrent, I specify my indices just a little bit differently. What's nice about this syntax is by specifying them all together, I'm able to give an assertion to the compiler that all of the iterations across I and j can be run in any order, which gives the compiler a lot of freedom in how it can parallelize the code. And so you can see we've done that with both of our loop nests here. And in terms of performance, you can see that we get good performance across a 2-socket Xeon using CPU threads, or you can also run on a GPU. And the performance of the GPU version using just do concurrent is comparable to a version using OpenACC. So you can see we've eliminated the needs for directives altogether and get comparable performance. Another Fortran application that I'll highlight here is Miniweather. Miniweather actually has C++ and Fortran versions, although I'll highlight the Fortran here. It simulates CFD calculations as they are relevant to climate and weather applications. It has existing versions using MPI, OpenMP, and OpenACC, and it is actually included as part of the spec Hpc benchmark suite, and that's why I've chosen the Fortran version here. You can see down below a sample from the code, and in this case, we've actually replaced 3 loop nests with 1 do concurrent, and this local clause, if you're not familiar with that, is for variables that need to be privatized to the iterations of the loop. In terms of performance, you can see that the do concurrent version runs roughly comparably to the OpenMP version across CPU cores, and roughly comparable to the OpenACC version when running on the GPU. And one more Fortran code is pot3d. And what's interesting about pot3d is it actually highlights what I was saying about being able to mix the different paradigms together. And so they had an OpenACC version of the code, and they decided to see what would happen if we took out all of the OpenACC and only used do concurrent. And they actually found that they got a reasonably good performance doing that, but it wasn't quite as good as the original OpenACC. They had about a 10% performance loss. And they started wondering, what might cause that performance loss. 10% was pretty acceptable, but they really wanted to find out the root cause. And what they found was, well, since the do concurrent implementation uses CUDA unified memory so that all of the data structures are visible on the CPU and the GPU, that they actually found that their code had a particular access pattern that was causing some of the data to migrate back and forth between CPU and GPU memory. This wasn't the case in the OpenACC version because they were manually, very explicitly moving their data. And so as a point of experiment, they actually added back only the OpenACC data directives, leaving away everything for their loops and focusing solely on the data directives like you see here. So all of their parallelism is exposed using do concurrent, and all of their data management is handled via OpenACC. And what they found is that they could actually get comparable performance using OpenACC for the data management and pure Fortran for the parallelism. So this is the type of situation where if that last 10% is important to you, then you could selectively mix in some directives to get to improve your performance. Or if this performance is already sufficient for you, then you can stick with that and still get great performance. So this is another spec HPC benchmark and a great example of how all of these paradigms can play together. So one last feature that I'll mention for programming the Iso Fortran is the importance of math intrinsics. So you can see here on the left a fairly naive triply nested loop matrix multiply. Matrix multiplication is a very simple routine to write, but actually kind of a difficult routine to get high performance because you need to really exploit all of the different levels of caches on your hardware to get the best possible performance. So rather than writing a triply nested loop, what can actually be done in Fortran is to write this matmul operation. And here this is exactly equivalent. It's multiply A times B, add it to C, and store it into D. And by writing it this way, rather than this naive inline Fortran, we're able to map it directly to our math libraries. And so you can get very high performance, the same kind of performance you'd expect by calling into something like kublas automatically. And you can expect that when new library improvements come out or new hardware comes out, that the performance will scale with those improvements. And so writing the code in this way lets you take advantage of all of the innovations of the hardware and software without making any code changes, and it's completely portable. And this is not just limited to matrix multiplication. There's a variety of math intrinsics that are available in the Fortran language that we could take advantage of. So far, I've discussed how you can program to the NVIDIA platform using the ISO standard languages. Now I'd like to address Python because Python has really emerged as an important language for high performance computing, AI, and data analytics. And so we're bringing GPU supercomputing to the Python ecosystem as well. So people choose Python because it is a very productive language. It's easy to understand, and you can write very high level productive code. But it'd be great to achieve high performance with Python as well. And we believe it's possible to actually accomplish both of these goals. So I've said that Python is considered a very productive language. And this code on the left is an example from a real application, and it's doing a conjugate gradient solver. It's using a package called NumPy, which is commonly used for mathematical operations in Python. What you notice here is there's really no visible parallelism, synchronization. There's no partitioning of data or distributing work. It all follows standard sequential semantics. This is just the way you write Python. And you can really compose it with any other Python library, and it just works. And so this code is really easy to write and easy to understand. But what's amazing is I'm going to demonstrate that you can actually write in this code on a supercomputer as well. Being able to productively program code like you saw on the last slide is important, but getting high performance out of it is important too. And we're delivering on software that will provide both of those capabilities, and being able to transparently run code like that at any scale that you have using whatever hardware that you have available. So maybe you only have one GPU. Well, that code should be able to run across that GPU. Or maybe you have a system like our DGX systems with multiple GPUs. And so being able to scale up to all of the GPUs you have. Well, what if you have something as large as a DGX SuperPod or some other large GPU cluster? Well, we can run that same code up to that scale as well. And in the future, maybe you'll have a Grace CPU or an NVIDIA DPU, and the code should be able to leverage those as well, being able to leverage all of the hardware that you have available to you. So Leagate is an ecosystem we're building to deliver on both of those goals, productivity and high performance. Leagate itself is a core library written in C++ that takes advantage of a project called Legion, which is a tasking runtime. Our intent with Leagate is to be able to layer on top of that a variety of APIs and be able to use Leagate to distribute the data structures and the work across all of the available hardware. The first package to show off what's possible is Numeric. Numeric aims to become a full drop-in replacement for NumPy. Now, we're not totally there yet. Numeric is alpha software at this point. It is freely available for you to try out. But there are gaps in functionality, and so if Numeric doesn't have the functionality you need out of NumPy, it will transparently fall back to NumPy for you. But using Numeric and other packages in the future, we're able to leverage what's possible with Leagate to scale your application to all available hardware. So as a proof of what we're seeing, this comes from a CFD code. The source code is available down here at this GitHub link. We took the code and as easily as changing the import statement, and so it no longer says import NumPy, but import Numeric. We could take the code and run it as is and actually be able to scale up to not just a GPU. You could already do that using CuPy today, but actually able to weekly scale it out to all of the GPUs we had available, in this case 1024 GPUs. So that's without any code changes beyond using Numeric in place of NumPy. We're actually able to scale all the way up to 1024 GPUs automatically. Here's another example. This comes from the scikit image library. So this Richardson-Lucy deconvolution routine here. And once again, all we had to do to modify the code is use Numeric in place of NumPy. So for instance, replacing the NumPy arrays with Numeric arrays. This code is otherwise unmodified. And what we see again is that the performance is comparable to CuPy on one GPU, but we can actually scale up to 1024 GPUs. And this is actually, once again, weak scaling, but this time showing the throughput increasing as we increase the problem size and the number of GPUs. And how does it perform when compared to a native version of the code? Well, this is using a join micro benchmark. The reason we chose this code is there actually is a hand-optimized version of this distributed join that was written by our Rapids team and is available online. And it takes about 1,700 lines of code with MPI and CUDA to get this dark green bar. That same benchmark can be written using NumPy and Pandas using just the code we see up here at the top. So this is the entirety of the benchmark code. And you can see that actually the performance scales quite comparably to that native code, but using just these high-level constructs in this high-level code. And Leagate is just one part of our broader Python strategy. So we do have CUDA Python, which currently provides official bindings to the CUDA runtime, but will eventually provide support for more of our libraries. And we also provide the Leagate core. But then layered outside of that are packages like Numeric and DataFrame that are able to leverage those APIs to provide support at a higher level. And then those APIs themselves can even be leveraged by even higher level packages such as Rapids, PyTorch, and TensorFlow. So this layered onion approach allows us to build out a strong base, a strong core that can be leveraged across the entire Python ecosystem. And now I'll shift focus and talk about the libraries that we provide as a part of our Hbc Sdk product. In terms of performance libraries, we have three primary goals for you. First is seamless acceleration. And what I mean is for hardware features like tensor cores or the enhanced caching that we provided in more recent GPUs, these should be leveraged automatically for you. So you don't necessarily have to understand how to program to the tensor cores on our modern GPUs in order to have libraries that support them seamlessly for you. Next, these libraries should scale up, not just supporting all of the GPUs that are available on your node, but in many cases now, we're actually able to scale up the library across entire GPU clusters. And lastly, it should be composable. They should work well together and work well with any code that you write in your application. NVIDIA has a huge set of math libraries. I've only highlighted some of them here, but many of them, the names are fairly descriptive as providing support for BLAS operations or FFTs or random number generators. And so if you're doing very common math operations, you should first check and see, is there a math library that does this? Because you get free performance that way. We have experts that are really tuning these libraries to provide the best possible performance on our platform. So if you're not leveraging those, you're leaving performance on the table. I mentioned seamless acceleration. This slide is meant to show you that many of our libraries, as listed down here, can leverage the various tensor cores and data formats that are available on our hardware for you, in some cases automatically and transparently. And so you can see here, for instance, Cutlass is able to leverage the tensor cores across all of these different floating point and integer representations. And so you can look and see the library that you are using and what tensor core support that it has already baked in. cuBLAS is our GPU implementation of the basic linear algebra solvers. It is a full implementation of BLAS, so vector-vector, matrix-vector, and matrix-matrix operations, but also has various extensions. Some of those are to support mixed precision, so using reduced precision or mixing precisions in the calculations, being able to run across multiple GPUs, or even batching. So if you have a lot of small matrix operations, batching them together into one kernel call to better leverage all of the hardware you have. And this is one of the most widely used libraries we have. A couple things here in terms of performance. We can see here comparing the Volta GV100 with the A100, and you can see here that if you can support the half precision matrix multiply accumulate, which is the FP16, that you can get a huge performance boost between Volta and A100. But maybe your code isn't able to support going all the way down to FP16. Well, on the A100, we actually have the TF32 format, which is not the strict FP32, but is a variation on that. And you can see you can get almost as good performance as Volta did on FP16 using TF32. Here I'm showing the cuSolver library. So whereas cuBLAS is the basic linear algebra building blocks, cuSolver is the higher level linear algebra solvers such as LU, Cholesky, QR, and also support for the various eigensolvers. Now, cuSolver can actually, under the hood, use techniques known as iterative refinement to utilize reduced precision math to still achieve full precision results. This is a very well-studied and well-understood technique to speed up your calculations by using the faster, lower precision in parts of the algorithm that are not as sensitive to precision. And so this technique is used in a variety of domains, in particular HPC and scientific computing. A feature I'll highlight here is the A100 GPU has what we call the DMMA instructions for double precision matrix multiply accumulate. And so you can use these tensor cores automatically in the library. So you can see the performance here comparing the V100 to the A100. You can see we're actually able to get a huge performance benefit because on the A100, the library automatically utilizes these hardware features to get the best possible performance. And so by using these libraries, when future GPUs come out, or when we simply make and discover additional performance enhancements, if you're using the library, you'll get those enhancements right out of the box without needing to make any code changes. In relation to using tensor cores automatically in our math libraries, here's an example from the Cutlass library. Cutlass is a C++ abstraction to matrix multiply routines. It's available on GitHub and as a part of our Hbc Sdk. Now this library is able to take advantage of the TF32 floating point format. And so what you see here is this black bar is what would be considered the FP32 peak performance on the A100 GPU. By using the TF32 format, we can map that to the tensor cores on our hardware, and you can see you can actually get a very high performance compared to the what would be thought of as the 32-bit peak. Now you might ask, well, what is the trade-off here? Surely the change in numerical format has some trade-offs in regards to relative error. And so this graph on the left shows you a bit about what to expect in that regard. And you can see that for increasingly large size of K, that in fact the relative error is better using this TF32 format compared to native FP32. So once you get up to a certain point, you're actually not just running faster, but getting more precise results out of this numerical format. Here is the cuSparse library. cuSparse has implementations for various sparse matrix algebra routines. Again, very widely used in HPC and scientific computing. And over time, we add new functionality and new algorithms to these libraries. So here, what the performance we're showing here is, we began shipping a new version of a particular routine up here, and this newer version is actually able to achieve a very high performance benefit over the old routine. So the library we ship does improve over time, and you can expect to see performance improvements over time. FFTs are widely used in a variety of domains, and of course we provide support for optimized FFTs on our GPUs, 1D, 2D, and 3D FFTs, including support for multi-GPUs. And so you can see on the right here, as the size of the FFT increases, you can see that we're able to support 1 GPU, 2, 4, or even here 8 GPUs of the same node, and you get pretty substantial performance benefits scaling it up as the problem size increases, utilizing all of the GPUs that you have available to you. Now, I mentioned at the beginning of this section that we're beginning to support multi-nodes in addition to multiple GPUs in the node on several of our math libraries. And so here's an example from the cuSolver library where we're able to scale up the performance across GPUs. So here we're running on up to 1,024 GPUs, and you can see that the cuSolver performance across multiple GPUs is actually better than the current state-of-the-art library that's available from the community. So this is generally available in the Hbc Sdk 2111 and beyond. It currently only supports a subset of cuSolver, but more functionality is constantly being added. We've also recently begun to support multi-node FFT libraries as well. So this is something that is in early access, and so if you're interested in trying this out, please contact me and we will see about getting you in the early access program, or you can visit this website. But you can see here on the left the multi-node version of cuSolver compared to the state-of-the-art community library running up to, in this case, 512 GPUs, and you can see that the cuFFT multi-node version runs quite a bit better than the version that's available from the community. And it also supports both FP32 and FP64 running out to all of these up to here. I'm showing up to 4096 GPUs. The initial release supports 2D and 3D slab composition. We are working on other compositions as well. So again, if you're interested in this, please visit this website or reach out and we'll get you introduced to our early access release. In addition to our math libraries, I'll point out that we have a variety of what I'd call core libraries. These provide the data structures and algorithms necessary to write your code. So Thrust is a library for parallel algorithms. It also has various GPU and host-oriented data structures. And the Thrust actually served as a basis for prototyping the support we have now for ISO C++ parallelism. libcuda++, or here you can see the GitHub repository is libcuda++, provides support for a subset of the standard library that is able to run on GPUs. And then cub is a group of cooperative primitives that you could use within your CUDA C++ kernels. In terms of the functionality these libraries provide, Thrust provides high-level container classes that you can use, for instance, a host vector, a device vector, a unified vector, high-level algorithms, many of which are now available directly in C++, although we do actually have some additional execution policies in Thrust that are not available in the C++ standard, and also some iterator classes that are used for convenience. Cub is collective primitives you can integrate into your existing code. It's often used inside of CUDA kernels for things like warp-wide, block-wide, or device-wide collectives. And there's also various utility operators available. So here is some examples here. Here I'm using two universal vectors. The universal vectors are visible both on the CPU and the GPU. And you can see that I'm issuing a copy and issuing a reduction operation here. And so this is a pretty high-level code that we've written here. And on the right, you can see that we're able to write reductions, which are notoriously difficult to optimize on the GPU. And you can see here we can actually write quite optimal version of a collective operation just using these building blocks. The third library I mentioned is libcu++, which is a GPU-enabled standard library. So by default, the standard library comes with your host compiler and its complete and strictly conforming version of the standard library. But if you want to use it on the device, many of the functionalities are just not available to you. libcu++ is a way of utilizing a subset of those functionalities on the GPU, and that subset is constantly growing. And there's two ways you can use it. There's the strictly conforming version where you have CUDA, STUD, and then whatever feature you want. Or some of them, and particularly some of the atomics, have some extensions that are not strictly conforming to the C++ standard. You can access those with just the CUDA namespace. And what's great about libcu C++ is it doesn't interfere with or replace your standard library. It's simply there for you to use on the GPU. And CUDA C++ is available not just in our Hbc Sdk, but also available on GitHub. And you can see here many of the features that as they became available over time, and some of the features that we'll be working on into the future. And lastly, I'm going to talk a little bit about our communication libraries. We do provide libraries that are optimized for communicating across the entire system. So not just with the GPUs within your node, but across entire systems, including low latency PGAS programming models, partition global address space programming models, such as NVSHMEM, and accelerated collective operations as well. So this comes as a package known as Hbcx, which is included in the Hbc Sdk. It provides native support for MPI and SHMEM using OpenMPI and OpenSHMEM, but also some accelerated packages such as UCX, HCult, and Sharp that can accelerate various operations by performing them on the network. NVSHMEM is a PGAS programming model based largely on the OpenSHMEM specification. And it is actually something that you can use from the CPU or the GPU. So your GPU kernel can actually initiate communication with other GPUs. You can also issue these communications in order with the stream, which has various advantages of being able to pre-issue the communications and into the stream as they relate to your CUDA kernels. And so this is something that's available as part of the Hbc SDK. And also Nickel, and Nickel provides optimized collectives. Initially, these were collectives on the node, among the GPUs on the node, but actually now can run across multiple nodes. And you can see here getting very high performance on the Summit supercomputer at Oak Ridge National Laboratory. So these can be used to really optimize the collectives, understand the topology available, and it is compatible with MPI as well. And then I mentioned tools earlier, and developers are only as successful as the tools they have available to them. And so we do provide in the Hbc SDK a huge range of tools, including CUDA GDB, but NVIDIA also has support for Nsight Visual Studio Edition to provide debuggers for you. In terms of profilers, Nsight Systems and Nsight Compute are the two products you see here that provide system level profiling and then also digging into specific performance characteristics of your kernels using systems and compute. And then there are also some extensions such as the NVIDIA Tools extensions, NVTX and Cupd. Compute Sanitizer is a way of checking for common issues such as memory leaks and race conditions. And then NVIDIA also has integrations into various IDEs, including Eclipse, Visual Studio, and most recently, Visual Studio Code. And you can actually download that from the Visual Studio Code Marketplace. So with all of that, I want to end with this slide to remind you once again that all of the things I've talked about are available to you through the NVIDIA Hbc SDK. And again, you can download this directly from our website or as a container via SPAC or in the cloud. So I encourage you to go download the Hbc SDK and begin utilizing these features that I've talked about today. And with that, I want to thank you for your time, and I'll be happy to take questions.
Awesome. Thank you, Jeff. So Jeff is on for everyone. If you'd like to ask questions, drop them in the chat box. You can ask directly. We have a few minutes to discuss. Please feel free to either raise your hand or however you feel best.
Well, if there's no questions now, if folks do have questions at a later time, you're welcome to email me, jlarkin@nvidia.com, and I can follow up with you then as well.
Awesome. That'd be great. And also, please feel free to drop them in the chat if you think of something as these discussions continue. We can also send them to Jeff later on. All right. Well, then let's continue with our next video. Our next discussion. So our next topic is Modulus. It will be presented by Sanjay Choudhry, and he is the Senior Director for Modulus at NVIDIA. As always, again, please feel free to put your questions in the chat box. We can address them directly during the presentation, or we can address them after the talk.
Hi, I'm Sanjay Choudhry, presenting to you NVIDIA Modulus, an AI framework for physics ML.
Modulus expands the scope of a toolkit formerly known as SimNet to all science and engineering domains. It is a physics-based machine learning framework to build solutions for digital twins of industrial systems, climate, protein modeling, and drug development. Each of these domains have unique requirements due to the breadth of governing scientific laws, and Modulus will bring to the developers the tools to build the solutions for each of these domains. One can see from this chart that there are 4 major application areas for Modulus. First, improved physics and predictions. Turbulence in CFD, constitutive modeling in composites, potentials in molecular dynamics, and radiation models in heat transfer all require modeling of micro-level physics. While the solvers can model the detailed physics very well, it is cost prohibitive to be able to use such models in routine analysis. Here, the neural networks can learn the micro-level physics that can be controlled by the solvers, which provide a cost-effective method for high-fidelity solution. Solution of inverse and data simulation problems using multiple physics types. Here in each of the examples shown, measured data from the sensor or imaging is combined with the governing PDEs to solve for the latent physics such as Navier-Stokes for blood flow or Helmholtz for wave propagation in FWI. The third is real-time simulations. In model predictive control applications with digital twins, robotics, and autonomous driving, decisions need to be made in real time based on the incoming data. Rapid inference capability of pre-trained neural networks provides the ability to do that. And fourth, digital design and manufacturing. Practically every physical product in any industry requires design analysis for optimized performance. Improvements in product quality, cost, or performance requires analysis of multiple design scenarios to be able to determine the optimum configuration. Examples from each of these areas are discussed in this talk, but first we present verification, accuracy, comparison, and performance data for Modulus. Modulus has been verified for several use cases and physics types against analytical, open source, and commercial solvers. The first example is that of a lid-driven cavity, which is solved using steady-state Navier-Stokes equations for both laminar as well as turbulent flow. Comparison with open foam shows a good correlation between velocities as well as pressure. Next, a 3D bracket has been solved using Hookean elasticity for small displacements and strains. The results show good agreement with a well-known commercial solver for displacements and von Mises stress. The third example deals with the solution of 1D wave equation, where a comparison with analytical solution shows an excellent agreement. Verification of modulus results for an electromagnetics problem with a commercial solver, vibration problem with analytical results, and turbulence problem with spectral solver show an excellent correlation. Modulus uses accelerated linear algebra, TensorFlow 32 precision, and automatic mixed precision features to accelerate the performance on a single GPU. Both the TF32 and AMP use the tensor cores on the GPU. The chart on the left shows a single A100 GPU speedup over V100 GPU. Using an FP32 precision, the A100 is about 1.5 times faster than the V100, but this speedup becomes 3 times or more when using TF32 precision. The TF32 comparisons with FP32 show similar level of accuracy with 2 to 4 times the performance improvements. Similarly, the use of AMP speeds up the training time by 2x or more. For parallel runs, both strong as well as weak scaling have been optimized. The weak scaling consists of accommodating larger workload, that is more points and larger batch sizes for increasing number of GPUs. As shown in the figures, the number of points increase linearly while the time per iteration is nearly constant with increasing number of GPUs. With addition of more GPUs, more points and large batch sizes can be used to enable solution of large problems. Strong scaling performance is shown up to 512 GPUs. However, due to smaller size of the workload, the inter-node communication dominates for use of more than 4 nodes in this use case. In case the workload is fixed, a linear exponential learning rate enables speeding up the solution. These improvements are crucial in case of solving large industrial problems. Very surprisingly, there were several problems where deep learning methods produced better results than the numerical solvers. These will be taken up next. It is demonstrated that even for simple geometries like the channel without the heatsink or an FPGA heatsink, The results from numerical solvers can be heavily dependent on the mesh size and quality. As the mesh is refined, the solver results converge towards the modulus results, which use point clouds to do the modeling. A conjugate heat transfer problem is solved using a 2D geometry where air enters the channel from the left-hand side and leaves from the right. The air cools the solid, which has a heat source at the bottom. A decoupled HFTB algorithm is used in Modulus, and the results are compared with a commercial solver. It can be seen that while Modulus satisfies the continuity of temperature at the fluid-solid boundary, the solver does not. Again, this is most likely due to mesh resolution, but clearly one needs to be really careful in a mesh-based solution regarding the accuracy of the solution. We look at the inverse and data assimilation problems next. The inverse problem is useful in cases where the partial or full field measure data is available, but the coefficients of the PDEs are not known. The coefficients once calculated can be used for forward solutions in various other scenarios. The concept can be demonstrated with a 2D example involving conjugate heat transfer analysis consisting of advection diffusion equation along with an interface and boundary condition. The results from a forward analysis using OpenFOAM are used as proxy for the real data, and an inverse analysis using Modulus is used to predict the coefficients like kinematic viscosity and thermal diffusivity. The next example involves data simulation in a medical imaging of intracranial aneurysm, where the data from a 4D CT scan or MRI is used along with the Navier-Stokes equations to calculate the wall stresses, which can then be used to estimate the probability of fatigue failure in the blood vessel after a certain number of cycles. An STL geometry of real patient's aneurysm and blood vessel is used to create the point cloud and boundary conditions needed to solve the problem. A transient flow is simulated over the entire time period. It can be seen that the Modulus results compare well with the OpenFOAM and Nectar results. Modulus results agree better at the aneurysm wall junction with the Nectar results, which uses higher order interpolation. The OpenFOAM results improve with the mesh refinement, but they still do not match the quality of the other results. SimNet training can be significantly accelerated using the transfer learning approach. When simulations have been carried out for a specific reference geometry, a new geometry using the same physics starts with the network trained on the reference geometry. This significantly reduces the training time due to fewer number of iterations as seen here. So we'll start with some examples of digital twins. This example is courtesy Professor Felipe Viena at University of Central Florida, where he and his research team used NVIDIA Modulus in building a digital twin of an aircraft cabin. Digital twin model is built to predict damage and fatigue crack growth in an aircraft window panel. An RNN model uses Modulus physics node to ensure the accuracy needed for prognosis and health management of structural materials. Once the neural network is trained, it can be used to perform fast and accurate computations as a function of different input conditions. With Modulus, they could scale the predictive model to a fleet of 500 aircrafts and get predictions in less than 10 seconds, as opposed to taking a few days to weeks if they were to perform the same computations using high-fidelity finite element models. A comprehensive summary of this study can be found at the PHM Society website referenced by the URL. Modulus results are compared with a well-known nonlinear finite element solver, and it is worth mentioning that Modulus achieves a level of accuracy that the commercial solvers could achieve only after a very high degree of mesh refinement. Digital twin of the Earth is a grand challenge problem that NVIDIA partners are using Modulus to build a solution for. Some of the early studies involved input consisting of 10 terabytes of ERA5 30-kilometer resolution state-of-art Earth system dataset, performance with resolution 6 times higher than state-of-art deep learning emulation, and speed that is 100,000 times faster than traditional principal numerical weather predicting models of comparable skill. and accuracy that is comparable or better than the state-of-art NOAA National Hurricane Center forecast for hurricane track and intensity. The scale and size encountered in building digital twin of the Earth would enable the framework to solve any industrial problem as well. Next, we look at design optimization. The example shown out here is an NV switch heatsink for DGX A100. In the heatsink design, the objective is to minimize the peak temperature at the source while satisfying the maximum pressure drop constraint. It is necessary to meet the operating temperature requirements of the heat source on which the heatsink is mounted for cooling. Modulus results compare well qualitatively and quantitatively with a couple of well-known CFD solvers. It is notable that the solver results were quite poor initially, but converged towards similar results eventually. Producing good results with a commercial solver took quite a bit of effort, as multiple runs with refined meshes had to be done. Modulus trains on parameterized geometry with multiple design variables in a single training run, thereby significantly accelerating design space exploration. In contrast, traditional solvers are limited to single geometry simulation. Once the training is complete, several geometry, material, or physical parameter combinations can be evaluated using inference as post-processing step, without solving the forward problem again. Such throughput enables more efficient design space exploration tasks for complex systems in science and engineering. The neural network in this example consists of 10 variables with minimum, maximum, and median values in the range of these parameters. Once trained, Modulus can solve the problem 10,000 times faster than traditional solvers.
Modulus is a framework for physics-based ML that can be downloaded from developer.nvidia.com/modulus. It has all the documentation, the source code, and examples with it. We plan to continue to release 3 times a year. The next release is end of this month, Modulus 22.03. Besides the new functionality, Modulus 2203 is transitioning from TensorFlow to PyTorch, which will allow contributions from academic and scientific community. With that, I'd like to end the presentation. Thank you.
Wonderful. So Sanjay is on. If you'd like to ask questions or drop them in the chat, please feel free. If there aren't any questions, we can continue. And if you think of anything, you can drop it in the chat and I can share with Sanjay later on. So the next presentation, or is there a question in the audience?
All right.
Is there a question? Okay. So our next presentation is Reservoir Simulation with Pins, presented by Clement Etienam, who is a solution architect on our energy team. Again, please feel free to put your questions in the chat box. We can address them during the presentation or after the presentation. And if you think of anything for either Sanjay or Jeff, please feel free to drop those in the chat as well, and I will share them after this discussion today.
Hi, I'll be giving a talk on physics-informed neural networks for solving reservoir fault and inverse problems. This work was done in collaboration with my colleagues here at NVIDIA, Pavel, Isam, and Ken. So I hope you enjoy this talk, and let's go. So I'll first start talking about first principle black hole simulation and why we want to replace that, and then some supervised learning preliminaries, and then we dive deeper into what pins are and how they'll be applied to reservoir simulation, and then some inverse problem, some novel application for Bayesian inverse problems, numerical experiments, then we conclude. So background knowledge, for reservoir simulation, we want to understand the flow and transport in the reservoir, and in it, the computational voxels needs to be pixelated. So you divide your model into small blocks, and then you solve for each block the conservation of energy, mass, and momentum for every block. So in principle, this is the way things are done, but it involves forming very large, sparse pentadiagonal or tridiagonal matrices that are used in the linear inverse problem, which in some reservoir requires enormous amount of memory to compute. So what we normally do is we form these pentadiagonal matrices, which, as I said, are necessary when solving this kind of inverse problem. And for a 2D case, we have this type of matrices, and T is the left-hand part of the Darcy flow equation that needs to be solved for every pixel and the surrounding pixel. So for the impulse method, we solve for the pressure implicitly, and then we solve for the saturation explicitly. And this is the kind of equation we normally solve. So this whole part here, this left-hand part, is your A matrix that you want to form. And the unknown for the next time step, the pressure, is solved using a linear inverse problem such as conjugate gradient, or even AMGX, which is NVIDIA's AMGX, or Gauss-Newton methods. But in principle, you have this AP equals to Q type of linear inverse system that you want to invert for P. And then the saturation is solved explicitly. So this is how things were done via first principle. But we want to replace this first principle with neural network. And the beauty of it is that it's meshless, and it is independent of the size of the reservoir, which is something that is applicable to reservoirs that that are occurring now. So the large sizes, it might take a while to forward each reservoir, and with the neural network approach, you don't have to use the whole computational grid. You could just take sample points, but we'll get to that very soon. So, but the background of supervised learning, which I feel is crucial to understand PINs, is you have an ansatz where you have labeled data, for example, X, Y, where I is number of sample points, so they're pairs. And you want to approximate this function given this parameterized by theta. So theta for linear regression is the mean and covariance. For neural network is the weights and biases. So think of theta as the parameter of your model or the machine. And the goal is to approximate this F so that for any future label data sets that is IID, which is independent and identically distributed, you at least have to, you hope that you have a semblance of good performance for out of sample or test data, as the case may be. So what I just explained is parametric models, meaning that you can hold the model itself. So you have some that are non-parametric, such as GP. So for a Gaussian process, you need to maximize the negative log likelihood for 3 hyperparameters, which are the length scale and the noise in the data and the covariance kernel itself. If you assume a squared exponential distance covariance matrix, you need to solve the negative log likelihood, maximize the negative log likelihood for that equation. Then for inferencing, you also need the training data, because any points between your training data is assumed Gaussian. So you need the training data that you used for any new sample points for inferencing. That's why GP is non-parametric, and it's not easily applicable because of the inversion of the kernel is in order n cube. So it doesn't scale well to large data sets although there are new methods that could be used, which I'm fond of, such as sparse Gaussian process or mixture of experts. But for this case, we focus on parametric model. So to optimize the theta, you could use the minimum norm expression here, just invert and get theta. You could compute the inverse using singular value decomposition, which is broken down into the left orthogonal matrix, singular eigenvalue, and right orthogonal matrix. So to get that inverse, if it's cheap and it's feasible, then you can invert for this and get theta, and you're good to go. But for any scientific application, and this method is we've done an implementation in NVIDIA for Bayesian neural networks or Bayesian pins. So the idea is if you pose your recovery of theta as a Bayesian ansatz, where your posterior density is based on the prior density and your likelihood function. So your theta here, assume, is your Taulton vector of your weights and biases concatenated into a vector. You could approximate the prior density given an ensemble of thetas, which are just the column of the matrix itself. So the matrix, the number of columns in the matrix is the size of the ensemble, and each member carries the prior density of your initial guess. And then your likelihood is going to be how far you are, given this initial guess, how far you are from your true label. So one method that can be used to sample the posterior density is the ensemble Kalman filter. So as I just explained, the mismatch between your data itself and the model itself. So you have two parts of your Bayesian inferencing. You have your model mismatch and your data mismatch, which is here. So your f of x given theta is your forwarding. That's from the forward problem itself, or from the forward model. And then this is your model mismatch. So your theta prior is your mean. That is, you get the mean of the matrix itself, just a singular column. And then you can solve for this with by getting the negative likelihood of this expression here. So the negative of this expression Q, which is given by this guy, if you differentiate this parameter with respect to theta and equate it to 0 to get the minimum of that cost function, then you get this Gauss-Newton like update. So your G is your gradient if it's available, and this term here is the innovation or the residual. This is how far you are from the true label. This expression here is known as the Kalman gain matrix. So the beauty of ensemble Kalman filter is you can replace your G if it's not available with covariances. So ensemble Kalman filter uses the first and second order moments, which are the mean and covariance. And by replacing this G, which is your Jacobian, by this expression for the covariance. So this expression here is the Hessian, and here is the ensemble gradient, and this is the ensemble Hessian. You can have the update term in terms of the covariance itself. So you get rid of the Jacobian matrices and you just use the covariances to update your theta for the next time step. So K is your iteration count. So this would stop if, according to number of iteration, or if you've converged or you've reached a certain tolerance range. So back again to GP. So GP, a Gaussian, the GP is a function of Gaussians. So sampled by a mean parameter and a covariance parameter, and we want to maximize the hyperprior on this covariance parameter, which are the length scale and the noise in the data and the covariance itself. And so sampling the posterior density of those hyperprior given your data. So your data is your X and Y is done according to this negative log likelihood expression here. And there are textbooks that can explain better how this can be sampled in principle. So we go into nonlinear models. So just quickly, nonlinear models, you have sets of neurons, and then you have a linear transformation, then a nonlinear activation function. Some could be ReLU, some could be tanh, some could be sigmoid. So the idea is that you can approximate a nonlinear function by very small linear approximations going on. So that's for nonlinear models. And then, as I said, for different cases, you have for regression and for classification, you have the for regression, the output layer is a linear function. For classification, is a softmax. In some applications, this is useful to get the probability of your prediction for different class itself. And then just repeating what I just said. So the loss function for classification is a cross-entropic loss. It could be binary for two classes or categorical cross-entropy. And the loss function for the regression is your mean squared error, your L2 mean squared error, and some regularizer. This is to make sure you avoid overfitting during your learning. So the updates, assume W is our theta now, but W is your weights and biases concatenated into a Tolton vector. So J is your iteration count. If you can somehow compute the gradient of the loss with respect to theta, you could update this. So what physics informed neural network does is that it doesn't have any label data. I assume you don't have label data like the case we'll see now. You can simply take the loss and get the gradient with respect to the weights using backpropagation. On TensorFlow is tape, on PyTorch is autograd function, and you can update the weights iteratively. So you could solve for this without label data if you know the physics involved, and it is hoped that if you know the physics involved in getting that data point, it can help in generalizing better, and it can even help in out of sample data set. There's a rigorous proof that shows that it actually helps in out of sample data sets. So in our application, we would have a pin, then we'll have a form of Bayesian neural network to help with giving some form of uncertainty in our prediction. So the pin for reservoir simulation without label data, in principle, we want to solve this two-phase flow problem. So this is the porosity, and S is the saturation. L is the number of phases, which is oil and water. The nabla is acting on this left-hand part, which is our T matrix. If you remember, this is the transputability matrix, and it equals to the effective permeability times the relative permeability divided by viscosity. The relative permeability is a function of the saturation using two-phase Rel-Perm curves. If you assume there is no influence due to height, you're solving for the pressure. So the pressure is the same in X, Y, Z in all directions. So this is just pressure, but the permeability is a tensor, and normally the permeability in the X and Y are the same, but the permeability in the Z is like 0.1 the permeability of X. F is your source and sink term given from Pisman-Well equation. Ideally, F is positive for injector because you're injecting downward, so it's positive, and F is negative for producer because you're taking out. So the system is closed by assuming that the saturation of the oil and water should be equal to 1. And if you don't have capillary pressure, so the pressure of the oil is equal to the pressure of the water. Now, so for us to solve that expression, we first have to break it down using a mixed residual loss function. So there's an elegant maths by Rasa and Kanadakis that shows that this kind of loss function is useful for Darcy flow type. So if you break down that expression into subparts, where this U is the potential now. So remember, if you don't have any height, if just a flat reservoir, then this can be ignored. So the potential is equal to the nabla of the pressure, and then the flux is given by this expression here, and then the nabla of the flux is equal to F. So using the mixed residual loss function, we see that the loss for the pressure CFD loss is given by the L2 norm of the sum of the flux and the Hadamard product of the permeability with the nabla of the potential. So the nabla of the potential is computed by using TensorFlow tape function in XYZ. So you just do a point-by-point modification of the k, and each components in X, Y, and Z. Now your t, you take the t in the XYZ. So assume this is for X direction. So it's Tx plus the tunability, which doesn't change, times point-by-point multiplication with the gradient of the potential with respect to the X direction. So that's for the X. You square that and square roots, and then you get one value. TensorFlow reduce mean, you get one value. You do that for Y, do that for Z. Then you need to also do for the F. So the nabla of the flux. So each flux is in the X, Y, and Z direction. It's just the sum of that minus F. So this would be minus minus if you're in the producer, and this would be as it is for injector. So that's for the pressure. Now the saturation is you do the same thing, but now you're computing the gradient, the change of the saturation with respect to time. Time is an input, and I'll show you the neural network as we go along. Multiply by the porosity minus this term here, this guy here. So you have two losses now for the CFD, and this is very crucial. This CFD loss mimics an impulse-like, or you can say fully implicit, but this is, I'm thinking of impulse now. So the pressure is solved and then the saturation is solved because it's a coupled system. So these two losses would account for the CFD loss. Now, we assume the flow is from left to right. It doesn't go from up to down, it's left to right. So if you assume there's a aquifer by the left of your reservoir, so you have an infinite pressure acting on the left, you could make that pressure fixed, or you could give it to 0. The left and right of the computational domain is a Dirichlet, so you can fix the pressure there, and then you can fix the flux. So the flux in the y direction, which is this guy, is fixed to 0 because you don't want the flux to go above. You have imaginary cells at the boundary, so you want to fix that flux to be 0. But the flow between layers is permitted, so you can. If we normally inject, if we assume 3 layers, for example, we inject 2 at the last layer, then the water rises up to the top layer, pushing the oil as we go along. So this is the crucial CFD loss function that will be added in our in the pin to get to backpropagate on the weights and bias. So the initial condition is the saturation of water and saturation of oil. So for initial time step, at time t equals to 0, you have more oil than water. So the saturation of oil will be 0.8, for example. Saturation of water will be 0.2. Then at the final time step, there's an endpoint. So the saturation of water at the final time will be 0.8, and the saturation of oil at the final time is 0.2. So with this initial condition, with the CFD loss, with the boundary condition, and then solving for the interior points and injector and producer, and I will show you how did we get more points at the producer, because the producer is just a pixel. But if you can build a supervised learning ansatz that can approximate your pixel value, which is your XYZ, around your well location to the permeability value, you can then sample more points. So sampling more points around the injector and producer is very, very crucial, because having just one point is non-informative to the neural network, but you want to have more points around, which is just a slight perturbation of your XYZ around the well. And I'll explain as we go along. So now, with label data, you could add, again, just repeating from the prior slide, you could add, if you have your labels of the pressure and saturation for every time step, because we're solving for the pressure and saturation, you could add that as an added loss function to your CFD, initial condition, boundary condition, final time. So you could add your labeled data loss or your supervised loss to that. So there are 2 ways you can go about it. Either you have with label data or without label data. But for this talk, it is without label data. Now, to approximate those points around the injector and producer, and this is very crucial. So I found out that I had to approximate more points around the injector and producer because I wasn't getting the dynamics of the flow of the water from the injector to producer. So you assume ID labeled sets again, and then the idea is that for discontinuous function, like the case we have in permeability fields or even pressure saturation, where you have a very sharp boundary, I developed a method called cluster classify regress during my postdoc with my former mentor. And the idea is that you first cluster your label, your data points to get labels. So if you bring your X and Y together, you have labels on the right. So that's just done. So, but to get the size of the clustering, we use what they call the elbow method. So the elbow is an L2 criterion that takes from 1 to, for example, 1 to 10 clusters. It sees the L2 loss for each cluster, and then the point at which there's a sharp bend, that is your optimum number of cluster that can cluster this XY pair. So once I built the labels using clustering, you can use k-means, you can use Gaussian mixture, or any method you want. But I found out that k-means is the one that is most likely feasible for very large data sets. So you cluster first, then with that X and Y, I kept the Y away, and then I built a classifier with X and L. So you can build a classifier using parametric or non-parametric methods. For this application, I use the XGBoost, extreme gradient boosting approach, which is a gradient boosting approach that uses classification and regression trees. There are papers there on it. You can use a deep neural network as well. So you just have to build a classifier, and then after building the classifier for each class, you build independent regressor. So think about the classifier as a manager that directs how much and who should go to where. Then the direction is called your experts. So you build independent experts, which could be polynomial regression, Gaussian process, or even deep neural network. But the manager is the classifier. And for a deep neural network, the last layer of your deep neural network, which is your softmax, can be used as a manager, or can be used like a gate. So it's called a gating network. And the direction it gives, you need to also build independent regressors for each of them. And for this application, I use the polynomial regression degree 3 with Hbcx function. All this is just to make more elegance, to scale. So there's some scaling and to make the data between 0 and 1. It's simple scikit-learn min-max scalar. And then I also decided, okay, there's a Bayesian approach, but it's independent of this work. But there's a Bayesian approach, which is a submission to a journal. So instead of doing that step by step, so what we just did was we clustered, we classified, we regressed. It's ad hoc and works, but there is a full Bayesian mathematical approach where the posterior density of your theta and the labels given D, and your theta in this case is the theta from your classifier and your regressor, all concatenated into a tall thin vector, is proportional to the product of the density of the likelihood given that particular regressor, that particular classifier, multiplied by the prior. So you have your prior classifier, your prior regressor, then the output from the softmax times the regressor itself. So if you multiply the output of the softmax, which is the classifier, times the point-by-point multiplication, so you multiply that output of the softmax times the value from the regression, and then you subtract from the y using an L2 norm cost function. Now you could sample your theta with any fully Bayesian approach like MCMC or even ensemble Kalman filter, but I prefer the full MCMC approach, the precondition Crack-Nicholson MCMC. So with MCMC, fully Bayesian, you could get you could sample this posterior density in principle. So that's about CCR and about Bayesian CCR. Remember, this was done for us to refine the points around the injector and producer. So we needed to get those points around the injector and producer. So now the architecture that I used for the reservoir simulation, I have 12 inputs for 12 outputs. So the 12 inputs are the XYZ, the coordinates XYZ. The KX, KY, KZ is permeability in the XYZ direction. This is the porosity, phi, and then T is the time. Then I set a range of the maximum well radius and the minimum well radius from literature. Then I set a range for the skin. Skin is between 0 and 1. So 0 means no skin, which is a brand new well. 1 means the well is deformed. So the skin is just level of deformation to the casing or the producer casing or the production tubing that can reduce the or impact flow during your drawdown. Your PWF is the work phase pressure, which is almost similar to the bottom hole pressure. And then for most times, the injector is controlled by the injection rate. So you know the rates, but you're trying to estimate the bottom hole pressure of the injector. For the producer, we fix the PWF and we try to get the rates that comes out. And then, so this PWF is tilted towards the producer, and then this injector rate is tilted towards the injector. Now, the outputs are for the oil and water. So there are 6 components for the oil and water, each for the oil and water. So the pressure, the saturation, the flux in the X direction, Y direction, Z direction, and then the change of the saturation with respect to T. This should be T, pardon me. This should be dS over dt, not dW. So dSO over dt and dSW over dt. So the left-hand part of the saturation change with respect to time. Now, the idea is that by computing the pressure, so the output of the pressure is used to compute this flux, because d over dx pressure is equals to the flux itself. So the nabla of that pressure is equals to the flux. In principle, the nabla times K times the nabla of pressure is the flux. So now, if you compute that flux with this pressure and compare with the flux that you're outputting, you hope that what you're computing in the neural network and what that is being spat out would be the same. So maybe if we have more talks and I could share the Python scripts, I was computing the flux, and then I was outputting the flux, and then that was part of the loss function also. And that the same was for the other fluxes and the other saturation. And then I was also computing SO plus SW equals to 1. So the saturation must be equals to 1. So the oil saturation must be equals to 1 minus the water saturation. And then the water saturation will be equals to 1 minus the oil saturation. So those were the losses that made up the CFD itself. So we've got to go through this quickly. So the algorithm is you have these interior points, and then the X for the interior, producer, injector, initial time, final time, boundary conditions. Those are the X. So the X's are those 12 features I just showed you. Now we learned our CCR machine, which is this the cluster classifier regress that I just explained. So this is just F is the regressor machine, C is the classifier machine. And then FK in principle, which is this your F, was for mapping XYZ to K. So I wanted to map my XYZ, that's the location around that injector and producer, to get a K. Then I could augment it. So once I get the K, I can get the porosity. So that's just the idea. So while you're less than a certain iteration count, or your loss function, is still, as far as your loss function is not less than this tolerance, do this. So I initialized the feed-forward neural network, which is that what I just showed you from the previous slide. And then I augmented my sample points around my producer and injector. And then I computed the rate permeability using Cori two-phase flow. And then I computed the K. So the K is the effective permeability times rate permeability divided by the viscosity for each of oil and water. And then the oil Cfd was given by that expression there that we just came from equation 12 and equation 12b. Where F is -1 for the producer because we're taking something out, and 0 for the interior point. So the CFD loss has the interior points, injector and producer for oil, and also boundary conditions. So all these 5 sets for oil. So you have the interior points, producer, injector, initial time, final time, and boundary conditions for oil, and then for water. And then if I had true data, for example, Y true, which is your true pressure and saturation field, you could also add that using the output from the neural network. So the L2 norm cost function that was added also to your overall phi. So your phi is your, as I said, the oil CFD, water CFD, initial conditions, boundary conditions, which is Newman and Dirichlet, final condition, and then label. If you don't have your label data, you could just go with that. And then optimize your theta for the iteration count using LBFGS or Adam. So for what the results was, I'll show you soon, we're optimized with LBFGS. Some I used Adam so you could have a Lagrange here by the left, as a weighting. So the Lagrange could assign different weights to different loss function. So I use Adam to optimize for that. Then I use LBFGS to go down more. So because LBFGS, you can be stuck in a saddle point. Adam would, make you jump out from that saddle point when it's looking for the cost function. And then LBFGS can finish up the job. So I combined Adam with LBFGS for another application, but not for the results here. Now for the inverse problem for reservoir simulation, the bulk of my PhD was you want to have a realistic inversion for your permeability, the effective permeability and the absolute permeability and the effective porosity. So you want to enforce geological realism. You want to have predictive power. So that's the aim of solving inverse problem. If we can match the past, you have a model that the confidence is high for future prediction. So in principle, this is mathematical answers here for a gradient-based deterministic inverse problem. So your G is your gradient, and then you need to invert for the G to go to the left-hand side. To get the inverse of this G is just done by singular value decomposition, where you have your left single eigenvalue, left eigenvector, singular eigenvalue, and your right eigenvector. So the transpose, a simple inversion of the singular eigenvalue, truncated singular eigenvalue. So what we do is that we get the energy where 99.9%, because the smaller the singular eigenvalue, the rougher the reconstruction. So Albert Reynolds in his paper did a truncated singular value decomposition method for inverse problem, and he showed very rigorous lemma that if you truncate the singular eigenvalue, you aid or you help the reconstruction more. So that's for if the G is available. But for what we do for scientific computing, I'm of the school of thought that it is good to have some form of uncertainty quantification. So upstep the Bayesian approach for solving inverse problem. So first of all, we need to get our prior, and then our prior permeability maps goes from a training image using a digital outcrop modeling approach. So your TI will give you different sets of permeability field or porosity field. This is geostatistics in principle. So if you have that, now the regularized ensemble Kalman inversion is the L2 cost functional. The cost function is getting the minimum of this L2 cost functional, where your T is your covariance matrix and your Y is your true data. So if you take all the data from the well or from your seismic and make it into a tall-thing vector with the U. So the G of U, your U is your unknown here, and your Y is always corrupted. So you have some form of noise there, which could be sampled by a Gaussian, given this unknown covariance matrix. So it's always unknown. The Wallner ensemble Kalman inversion by Andrew Stewart and Iglesias solves this method in this function this way. So your probability at the next time step is equal to the prior, and then your covariance matrix is similar to the ensemble Kalman filter. So now the new approach we developed in NVIDIA was to get this alpha parameter using Jeffrey divergence and discrepancy principle. So we developed a method internally that could approximate your alpha in a quicker method. So the algorithm here is you have your initial ensemble of inputs, which is your probability and porosity field, and then while your loss is less than 1, you compute regularizer parameter, you check for the convergence using a method you see in the next slide. So the method is, I compared the maximum between m over 2 phi tilde n and the square root of that expression there. So m is the number of sample points, and then phi tilde is mean, and this time for the standard deviation. So the maximum between this expression was held, and then I compared the minimum between this expression and 1 minus Tn. So there's rigorous proof on this new method, this new approach. Because it's a tempering approach, I'm going softly from ui to ui plus 1. I plus 1 could be the converged solution. I had to use this tapering alpha method. So alpha dampens the denominator of the Kalman gain. So for more information, you could contact me. My email will be in the program. You could contact me, and then I could show you more as to how this converged and how this works. So now, another thing that I played around with was combining Ksvd and orthogonal matching pursuit. So for dimensionality reduction is an inverse problem. You want to make it less imposed. There are other methods that could be used: discrete cosine transform, singular value decomposition, principal component analysis. But for here, I use the Ksvd and orthogonal matching pursuit. So Ksvd was done by Dr. Aaron in Ben Gurion University, and OMP takes it from spatial to sparse. So you want to convert a probability field from spatial domain to sparse domain, which is more which makes the inverse problem less imposed and reduces the computational complexity in the Kalman gain. And then at the same time, when you're done, you want to back transform back to the spatial field. So this is how Ksvd is. You have your true spatial probability field, and then you have your dictionary that is your forming column by column, and then your X is the sparse representation of your Y. So Ksvd is done with a two-step approach. You first k-means clustering, you freeze D, update X, freeze X, update D, back and forth. For more information, you could check the the paper by Aaron. So orthogonal matching pursuit is a greedy algorithm. Greedy in the sense that it gives the greediest approximation to your residual here. For example, if you have a change of, like, say 30 pounds, you could either take it in 5 pounds, or you could take 20 and 10 pounds. So OMP takes that 20 and 10 pounds analogy here. It forms the X matrix that is greediest in solving the L2 cost functional, the L0 cost functional, sorry, not L2, the L0 cost functional in your residual. So this is just another ansatz for Ksvd and how it works. So now back to the experiments. This have a computer by root mean squared error to show how good we are in our logic. So I call it the ML history matching logic. Remember, we have our pins that does our forwarding. So you have your input, which is your training image. You use DOM, digital outcrop modeling, MPS. You get your initial ensemble. Then you learn your Ksvd over complete dictionary, and then you don't do it once and offline and keep it in the folder. So during history matching, you're forwarding, you solve the forward problem with the pin that we just developed. So the pin replaces our forward model, and then we form covariances, and then we convert our permeability field to sparse domain using orthogonal matching pursuit. We update the coefficients of that OMP, and then we back transform to spatial. So this goes on and on until the convergence. As I just said, so you have RecI with Ksv OMP, so the sparsity promoting history matching, and our forward problem is solved by the pin itself. So the numerical experiments, on the left is your impulse approach here. Your triangle is your producer, the one facing upward. The one facing downwards is your injector. So you can see that there's still a little bit work to be done in the resolution around the injector and producer, but it's similar in the sense that you're injecting water at the edges, and then it's pushing the oil towards the producer. So the left is the full finite difference approach. The right is the pin. The error bar was very, very low, although I didn't show it here, but you could see that both of them obey the same physics in pushing the oil towards the producer. So this gave me confidence in using this as a forward model during my history matching approach. So the toy model I wanted to solve was the probability field 33 by 33 is highly channelized. Highly channelized. I have 4 producers, 4 injectors. Submission is for 2,340 days, and all the NVIDIA lovely packages, CUDA, CuPy, Number, they were all used in all this. So cuDNN was used for training. As we speak, I just ported my code into Modulus. cuDNN was used, CUDA was used, Number was used, CuPy was used. This gives accelerated computing, and without using this workhouse, I had a 40 times speed up in my training of the pin was 40 times faster, and then my forwarding, because it's in parallel, was about 25 times faster. And the solution to the inverse problem, although that is indeterminate of whether you use parallel computing, but the forwarding, which is crucial for ensemble Kalman filter, was faster than using just a CPU, using the cores on the CPU. So so this is the toy model I want to recover, or we want to recover. On the panel C is without any fancy deep neural network parameterization. Focus on panel B. So panel D is the true, and panel B is the recovered using the in this case I use ESMD or RecI. It's almost similar, but I think this was for ESMD. And then to the denoising convolutional autoencoder that was used to get that recovery. So in history matching, we also check, boring things like this. If you look, the right is the initial ensemble. You can see it's big and fat and not that good. And then the left is the ensemble that has been tuned or recovered, and see how slim it is. Uncertainty has been reduced, and this model is good for predicting the future. Similar to this, this panel here, and you can see RecI doing a good job. RecI and ML doing a good job to recover the true, which was a very rigorous channelized reservoir. And then the loss cost function value. So RecI had a 0.32 compared to 36.31 and 9.42 without any initialization. In all this, the pin was used as a forward model. So in conclusion, we developed a physics informed neural network that solves Blackwell model It approximates the pressure and saturation field for any input of permeability and porosity. The neural network was a fit for neural network. The weights and biases were updated with LPFGS. The output were the pressure, saturation, and fluxes. And then compared to the first principle black hole, it was very, very similar and close. And then Rekai was used to update the Fashi. We had a it was very, very fast, just 30x speed up to finite difference, as I said, for inferencing, not for learning. It took 35 minutes to learn with 7,000 samples of pressure and saturation field. Future work will be to add time and added input for compositional flow simulation. So these were just for Blackwell, and then the idea is to use it for compositional simulation in the future. These are some references for history matching, ensemble smoother, and then for other methods on Kalman filter, Rekai, and also on pins itself. So thank you very much, and I can entertain any questions now.
Great, thank you. So please feel free to drop questions for Clement in the chat box, or you can ask directly. If there aren't any, we can continue. If you think of something, or if you have any questions later, please feel free to reach out and we will get them answered for you. For some reason.
Hello, everyone. My name is Kashif Chauhan. I'm Solutions Architect with NVIDIA. Thank you for joining this session today at 2022 Annual Rise Energy HPC Conference. Today, I'm going to talk about a topic that should be of interest to anyone deploying GPUs. This relates to optimizing data and storage movement for machine learning and deep learning. As AI becomes increasingly pervasive.
One moment, for some reason the video is not working. Let me see how I can.
Hi, Nefeli. If you can't play it directly through the video, you can also share your screen and play it that way if that works.
I did try that, but the video itself is not showing for some reason. That's the issue. I'm not sure why it was working when we checked yesterday. One second.
I know we have Kashif on the line. Do we want to just have him present it live then?
Let me just double check one more thing, and I apologize for the delay. Yeah, 1 second.
Everyone you can take a quick break and grab some coffee if you want to right now.
Okay, great. We're back up and running. Sorry about that. So our next talk, let me share my screen, is titled Optimizing Data and Storage Movement for GPUs, presented by Kashif Chauhan, who's a solution architect for NVIDIA. So again, please feel free to drop any questions that you have in the chat box. We can answer them during the presentation, or feel free at the end to raise your hand and ask questions. So let's go ahead and kick off.
My name is Kashif Chauhan. I'm Solutions Architect with NVIDIA. Thank you for joining this session today at 2022 Annual Rise Energy HPC Conference. Today, I'm going to talk about a topic that should be of interest to anyone deploying GPUs. This relates to optimizing data and storage movement for machine learning and deep learning. As AI becomes increasingly pervasive in our professional and personal lives, and as the scope of HPC expands beyond traditional sciences and research, we're dealing with data sets in units like zettabyte and soon yottabyte, units which are even difficult for us to comprehend as humans. Yet we continue to generate and collect data at an ever-growing speed. This ability to generate and gather data at an increasingly faster pace, leveraging more accurate sensors and large-scale simulations, is enabling us to break the boundaries of science and do things we had never imagined possible. These datasets give us the opportunity to understand the universe around us, make intelligent decisions, and do research at an incredible pace. Right in the heart of this incredible research is NVIDIA. The growth and success of artificial intelligence is impacting every corner of our lives. Fueled by enormous computing power of GPUs, new models are larger, more accurate, and achieving almost superhuman accuracies. And of course, computing and storage go hand in hand. Just as computing demand has far exceeded the capacity available in a single server, the storage demand required to match the computing power must also be met. The fastest computing on Earth won't scale unless you can move, access, and manage data. Therefore, in addition to accelerated computing on GPUs, NVIDIA now offers solutions for memory, network, and storage bandwidth. Solutions that allow you to get the most out of your infrastructure and as fast as possible. All of these are part of the Magnum IO suite. As far as today's agenda, my objective is to help you get the most out of your machine learning and deep learning investment. To that end, I would like to share with you a couple of interesting technologies offered by NVIDIA. Technologies that can help you leverage your data set in the most optimal manner. Technologies that can eliminate system and storage bottlenecks to enhance your application performance. Be it machine learning like RTM for seismic imaging or deep learning like NLP. First area of optimization that I would like to cover is the family of NVIDIA GPU Direct technologies, with particular focus on the newest member of the family called GPU Direct Storage. But I'll preface that with GPU Direct RDMA and GPU Direct Peer-to-Peer. Second area of enhancement that I would like to cover is an innovative adapter card architecture called multi-host. Multi-host and its variant Socket Direct allows CPUs within a multi-socket server to connect directly to the network through its own dedicated PCIe interface. This increases network and storage throughput while reducing latency overhead and CPU utilization. A few words on Magnum IO stack before we go any further. Magnum IO hosts a lot of performance capabilities that we'll talk about here. As you can see in this diagram, Magnum IO serves as the data foundation interface that CUDA and CUDA-X libraries use. Therefore, Magnum IO, as the IO subsystem of the data center, serves as the foundation for data movement, access, and management. The name Magnum IO is derived from multi-GPU, multi-node input-output. Inside a data center, there's a hierarchy of resources across which data must be managed. There's a hierarchy of computing, memory, and storage resources at the GPU, node, subcluster, and data center level. User tends to just want their data, so access, management, and movement of data across all NVIDIA GPUs and NVIDIA network needs to be controlled and abstracted through a varied set of APIs, libraries, and programming models that NVIDIA offers. This is all handled by Magnum IO. AI relies on datasets, large datasets, very large datasets. As useful as these datasets are, it can be challenging to leverage them if not deployed in an optimal manner. The challenge is actually making the local and remote data available to GPUs as fast as GPUs demand it. Addressing these challenges mean eliminating as many bottlenecks as possible that exist between GPU to GPU communication and storage to GPU communication. And this is where NVIDIA GPU Direct families of technologies can create a significant impact. First, allow me to refresh your memory on a couple of older members of GPU Direct family members, GPU Direct RDMA and GPU Direct Peer-to-Peer. After that, we'll focus on the newest member of the GPU Direct family, GPU Direct Storage. Starting with GPU Direct RDMA. Originally introduced with Kepler class GPUs and CUDA 5.0 almost a decade ago, GPU Direct RDMA enables peripheral PCI devices direct access to the GPU memory. GPU Direct RDMA provides direct communication between NVIDIA GPUs in remote systems. As you can see in this slide, communication without GPU Direct RDMA depicted with purple lines, data must first be bounced into CPU system memory from GPU using CUDA memcopy and then be bounced out to the adapter card. This traversal through the bounce buffer creates a bandwidth bottleneck, increases latency, and increases CPU utilization. With GPU direct enabled, on the other hand, as shown with green lines or arrows, data can be copied directly between GPU memories without engaging CPU or CPU memory. This significantly increases data throughput, reduces latency, as well as it reduces CPU utilization. Here you can see comparative throughput with Hbcx MPI on a 100 GPU with and without GPU direct RDMA. Black line is without GPU direct RDMA. Green line is with GPU direct RDMA and GDR copy. You can begin to see the difference of almost 10x as message size increases around 1024. Additional GPU direct RDMA performance metrics from Selene cluster, the 7th largest cluster on top 500 list, which is based on GPUs. Here you can see a minimum of double the bandwidth advantage with 8 endpoints pairs moving data concurrently. There is 122 gigabyte per second difference, 71 gigabyte per second without GPU direct RDMA, and 192 gigabyte per second with GPU direct RDMA. Significant difference. And here you can see the latency advantage, also almost 10x in the same environment when comparing with GPU direct RDMA and without GPU direct RDMA across almost all message sizes. Once again, additional data from the DGX A100 based Selene cluster, this time related to latency with GPU direct RDMA. We ran the Osu benchmarks to evaluate latency for 4-byte transfers. We used two main ingredients: GPU direct RDMA to avoid host copy at the sender, and GPU direct copy to accelerate the copy from CPU into the GPU at the receiver side. With both of these being used, latency dropped from 26.6 to 3.4 microsecond. Again, very significant reduction in latency. Now let's talk a little bit about GPU direct peer-to-peer. Compared to GPU direct RDMA, which optimizes GPU to GPU communication internode, GPU direct peer-to-peer enables intra-node GPU to GPU communication without engaging system memory for data transfer. GPU direct peer-to-peer allows CUDA to use high-speed DMA to copy data between two GPUs in the same system. In this slide, left-hand side represents memory copy between two GPUs on the same system without GPU direct. This requires data to be copied from GPU 1 memory into CPU system memory before it's copied to GPU 2 memory. With GPU direct peer-to-peer, on the other hand, as shown on the right-hand side, the CPU or system memory is not engaged. The data transfer occurs directly between GPU peers. Similar to GPU direct RDMA, this increases throughput between GPUs while lowering CPU utilization as well as lowering communication latency. GPU direct peer-to-peer has been part of CUDA toolkit since CUDA version 4.0. With direct transfer, CUDA memcopy initiates DMA from GPU1 memory to GPU2 memory as shown on the left-hand side. And with direct access, GPU1 reads or writes from GPU2 memory as shown on the right-hand side. I would like to highlight that peer-to-peer transfer is permitted between GPUs connected to the same PCIe switch. However, GPU direct peer-to-peer will not transfer data across QPI. In the topology shown here, GPU1, for instance, can perform peer-to-peer transfer with GPU2, 3, or GPU4. However, GPU1 cannot perform peer-to-peer transfer with GPU 5, 6, 7, or 8, as GPU direct peer-to-peer communication is not supported over QPI and between two I/O hubs. A transfer from GPU1, for instance, to any of the GPU across the QPI will require copying through the system memory of the CPU. As data sets have grown to unprecedented sizes, what appears to be the case is that as GPU is addressing the computing demand, I/O seems to be becoming the bottleneck. As shown on the top right-hand side, traditionally, developers would read the data into the CPU and leverage GPUs for certain accelerated workflows. However, increasingly more and more, in fact, complete workflows are shifting to GPUs, as shown on the bottom. This is great for computing. However, it introduces an I/O challenge for the data-hungry GPUs. At a high level, GPU direct storage, or GDS, allows you to enjoy the best of both worlds: capability to fully utilize the computing performance of GPUs, as well as the capability to ingest I/O that GPUs require. And GDS accomplished this in a relatively effortless manner, without requiring any special software or hardware. GDS is applicable to both local and remote storage. It is available as part of CUDA 11.4 with QFile API, which I will discuss further in a couple of slides. Allow me to first describe what the issue is and how GDS resolves this issue. Today, the only thing that Linux lets you do when you need to provide an address to which you can DMA is system memory on the CPU. Therefore, transfer of memory from storage to GPU must traverse CPU system memory, restricting bandwidth, increasing CPU utilization, and increasing latency. With GPU direct storage, as shown on the right-hand side, data is copied directly between local or remote storage to GPU memory, avoiding the CPU bounce buffer that we previously talked about. There are a few additional highlights about GDS as shown here that I would like to share with you. You can take advantage of GDS on a single node or in a multi-node environment. It is supported with Ubuntu 18.04 and 20.04, Rail 8.3, and Base OS 5.0 for DGX. GDS is also integrated in frameworks such as PyTorch and MXNet via the data loading library, and Spark and Rapids via the QDF library. GDS is available as part of CUDA 11.4, as I mentioned before, with QFile API, which I will dig a bit further into now. Now let me share a couple of charts comparing data transfers without and with GDS. This particular chart is based on 800 gigabit IB cards in the previous generation of DGX server, DGX2, which is being served remote storage on 4 Weka nodes, also connected with 100 gigabit adapter cards. Though up to 32K message size, there really is no advantage, but after that, you can clearly see growing throughput advantage with GDS, delivering double the bandwidth at 128K, triple the bandwidth at 256K, and almost quadruple the bandwidth starting at 512K. And here are some performance numbers on DGX A100 with 8 HDR adapter cards, accessing vast octanes for writes and QLC NVMe drives for writes. Similar to the previous chart that I shared, you have a growing bandwidth advantage of up to 3 times the bandwidth with GDS. You also can see that we are at 14% CPU utilization with GDS versus 49% without. And lastly, the latency is 12 milliseconds with GDS versus 52 milliseconds without. So not only there is throughput gain, but there's also a reduction in CPU utilization and lowering of the latency. Digging just a little bit deeper into the Qfile library to see what additional capabilities are provided by this library. It provides common APIs for both RDMA and local DMA-based storage. And it provides a common interface for both aligned and unaligned I/O. It tries to avoid intermediate copies when possible to achieve the maximum throughput with lesser CPU utilization. This library is also aware of the system topology and resources available with respect to NICs, storage, and GPUs. It provides configuration to tune file system-specific functionality and the GPU resources, such as limits on bar 1 memory and bounce buffer pool size. Other configurations include tracing, logging, blacklisting mounts, drivers, and file systems. To bypass the page cache, the file needs to be opened in ODirect mode. With compatibility mode, if the files are not open in ODirect, will fail to the POSIX mode. Digging just a little bit deeper into the Qfile library to see what additional capabilities are provided by this library. It provides common APIs for both RDMA and local DMA-based storage. And it provides a common interface for both aligned and unaligned I/O. It tries to avoid intermediate copies when possible to achieve the maximum throughput with lesser CPU utilization. This library is also aware of the system topology and resources available with respect to NICs, storage, and GPUs. It provides configuration to tune file system-specific functionality and the GPU resources, such as limits on bar 1 memory and bounce buffer pool size. Other configurations include tracing, logging, blacklisting mounts, drivers, and file systems. To bypass the page cache, the file needs to be opened in ODirect mode. With compatibility mode, if the files are not open in ODirect, will fail to the POSIX mode. Here we have a basic usage example showing the APIs to write data from GPU memory directly into a file. The first step is to open the driver, which performs configuration checks and registers with the available storage drivers. This step is performed implicitly when any of the Qfile I/O APIs are called. The second step is to open the file the Linux way, but with ODirect flag set. Next step is to register this FD with the Qfile subsystem to perform basic checks on the FD, including file system support and any unsupported flags on the FD. Once registered, you get opaque Q file handle that can be used for read and write. The next step is to register the buffer with Q file to open the bar1 mapping for this specific memory area. As we have seen before, there are performance benefits when you register the buffer, especially for smaller I/O sizes less than 512 KB. Once the buffer is registered, you can perform read and write similar to pread or pewrite. The rest of the code is to deregister the buffer and free up the handle to free up resources in the Q file subsystem. And this is a good practice to clean up. Now let's talk about yet another interesting, innovative, and unique solution offered by NVIDIA called multi-host. Multi-host enables direct connectivity from multiple hosts to a single network controller, allowing flexible and heterogeneous data center design with direct access to data while reducing capital and operating expenses. Multi-host technology allows for different CPU architectures, including x86, Power, and ARM, for instance. With multi-host, each host is kept completely independent from others. Hosts sharing the same network interface save on switch ports, cables, real estate, and power. This technology allows direct connectivity from multiple hosts to the network, enabling direct data access with lower latency and overcomes performance bottlenecks to maximize data processing and transfer rates. There are two main variations of multi-host card: the multi-host adapter card and the direct socket adapter card. I think it might be beneficial to do a quick high-level overview of both cards before I jump in. Let me start with a brief comparison of both cards. Then I'll dig a little bit deeper into multi-host with a case study and follow that up with a discussion on socket direct card. Each card offers certain advantages depending on the use case that you're considering. Multi-host card allows multiple hosts to share a single adapter card, just as the name implies. This is accomplished by splitting the PCI lanes on the adapter card. As you can see here on the left-hand side, we have a chassis with 4 nodes and a single adapter card. Multi-host is more directed towards reducing cost if your environment does not need a ton of bandwidth for network communication. Socket direct, on the other hand, is all about performance within a single server. This card also splits PCI lanes, but within the server to different sockets, thus the name direct socket. As we discuss it further, you will see that with NDR 400 gigabit, we have interesting options with socket direct and multi-host card. This allows for lower cost and higher performance. Frankly, both solutions are pretty straightforward, but the benefits are pretty significant. For multi-host card, there are a couple of different physical variations. Here is an example of a multi-host card where there are 4 nodes in a 2U chassis. Compared to the previous slide where I had shown a blade with a multi-host card that served 4 nodes in that blade. And here is an example of an external multi-host card. On the top is an example of a chassis with 4 nodes, and at the bottom is an example of 4 independent servers connected via external SAS cables, which can extend up to 50 centimeters. You can immediately see the cost benefits here. If 100 gigabit is sufficient for your network connectivity, you can use a single card to serve 4 nodes. Not only are you reducing the cost of adapter cards, you're also reducing the cost associated with cables, switches, and the required power. Another quick point I would like to make here is that in this example, I offered NDR as an example. However, this is also applicable to HDR, which result in 50 gigabit per second to each of the 4 nodes. And it does not need to be InfiniBand. This solution is also available with Ethernet. So you have a choice of InfiniBand or Ethernet depending on your fabric requirements. Now let's talk about some of the advantages that multi-host solution offers. First of all, as I mentioned, it is supported with both InfiniBand and Ethernet. There is also an option for VPI cards. For those who are not familiar with VPI, VPI cards are able to function both as InfiniBand and Ethernet cards. They default to InfiniBand, but you have the option to easily change that to Ethernet. As a matter of fact, you also have the capability to have, in case of dual port cards, one port function as IB and the other port can function as Ethernet. In the second bullet point, again, we're splitting 16 PCI lanes into 4 lanes of quantity 4. So here we can see that we have the main adapter card on the right hand, and we have 3 auxiliary cards shown on the left hand side. So we have 4 lanes going to each of these auxiliary cards, and it does not have to be for 4 lanes. If you demand more bandwidth, you have the option to have the cards split into 2. Another interesting part about multi-host card is that if you have traffic that needs to be within these 4 servers, it will be contained within the framework of a single multi-host card. You would not need to go outside of the adapter to the top of rack switch to come back to, let's say, communicate between server 1 and server 2, or between server 0 and server 3. Another point I want to highlight is that you have full end-to-end RDMA and RoCE capabilities, just as you would in a standard card. There's no difference in RDMA or RoCE from that perspective. Or for that matter, there's no difference in any feature and functionality between a multi-host and a non-multi-host card. You have full feature parity between a standard card and a multi-host card. And then we already touched on some of the cost benefits for multi-host, resulting in lower CapEx and OpEx. Here's an example of a 100 gigabit multi-host architecture that has been deployed by a large customer. The job in their environments were more localized and typically did not expand to more than a couple of adjacent nodes. So in their environment, each multi-host card served 4 hosts in a single chassis. Additionally, with a splitter cable, they split a single 100 gigabit port into 2 50 gigabit connections. This resulted in a single adapter card serving 4 hosts and a single switch port serving 8 hosts. Since the server were PCI Gen 3, with 4 lanes of PCI Gen 3, each auxiliary card is capable of bursting up to 30 gigabit per second if the bandwidth is available. Of course, with InfiniBand NDR or 400 gigabit currently available, you can deploy a solution like this to lower your fabric cost and still be able to deliver a significant amount of bandwidth to each node. For this particular customer, the cost savings were significant and immediate. As you can see in this table, they were able to reduce the number of switches by over 40%, reduce the number of cables by almost 50% and reduce power consumption by approximately 61%. A very similar solution, but with another customer with 400 gigabit NDR versus 100 gigabit Ethernet. As I just mentioned, with the availability of 400 gigabit NDR, the multi-host solution becomes even more attractive, as you can potentially serve up to 8 nodes from a single 400 gigabit switch port. In case of NDR, this could translate into 512 nodes served by a single NDR switch at 50 gigabit per node, or 256 nodes served by a single NDR switch at 100 gigabit per node. The next thing I would like to cover is the socket direct card. Similar to multi-host, it supports both InfiniBand and Ethernet. And similar to the multi-host variation that I previously shared, there's a single external connection to the switch. The main focus of socket direct card is performance. So essentially what we're doing is we're taking each of the card and placing it in a PCI bus in a different NUMA node. So each CPU has access to its own adapter card. So as shown here on the right-hand side, each CPU will talk to the PCIe card that it has direct access to, instead of going through the QPI, which would have resulted in a lower bandwidth, increased latency, and higher CPU utilization and overall performance degradation. And from application perspective, whether it's MPI, nickel, or any other application, these are perceived as two separate cards. As a matter of fact, to the OS, they will appear as two separate cards as well. Before I talk about socket direct with NDR, let me first explain basic NDR connectivity with socket direct. If you're looking for a standard 200 gigabit connectivity to the node, you can leverage 4x200 gigabit splitter cable and simply use socket direct card in each host. This is exactly what is shown here in the diagram. We have an OSFP port with 2 NDR ports. We have splitter cable that splits an OSFP port into 4x200 gigabit ports, one of which can deliver 200 gigabit to each of the compute nodes. The last thing I would like to share with you are some performance metrics for socket direct card. On the left, you can see some latency numbers. Figure 1 compares average latency of socket direct card with standard card in a dual socket environment. You can see that there's about 80% drop in latency with socket direct card compared to the standard card. Figure 2 on the right-hand side is looking at some CPU utilization numbers. And you can see that there is an overall decrease in CPU utilization by about 30% or so. With that, I hope you found this session useful. If you have any questions, please feel free to reach out to me. I appreciate you attending this session. Thank you very much for your time.
Great, thank you. And thank you all for attending. If anyone has any questions, please feel free. Oh, I see a question from Maram. I apologize if that is pronounced incorrectly. A question regarding GDS. Is there a certain parallel file system that GDS favors in any way? Be GFS over Lustre, for instance. Kashif, I believe that one's for you. Maybe he stepped away for a moment. Oh, there we go. Great. Does anyone else have any other questions for any of our presenters? Clement is still on, as is Kashif, and if you have any others, I can certainly send them to Jeff and Sanjay. Otherwise, I think we can wrap up. Thank you all for attending. Thank you to our presenters. And I hope you all have a great weekend.